welcome back. In this video, we're going to use the three trigonometric ratios to analyze a number of different right-angled triangles. Over here, we've got a right-angled triangle in example 1. We have known quantities of 14 for a side length here, and the angle of interest is 38 degrees. What we don't have is this unknown quantity here, x, so this side length here, and this other side length denoted by the variable y. What we're going to do is use the trig ratios to deduce the values of both x and y. Now, before we can do any form of calculations, we first need to label our triangle. The angle of interest we denote that as theta. Opposite the angle theta, we have the side O, or opposite, and adjacent to the side theta, or the angle theta, we have the side adjacent. Now, the final side we have is opposite our right angle, and it's our largest side, and we call it the hypotenuse h. Now, the next step is we want to calculate the side length here, so the quantity for x. So what I'm going to do is I'm going to write out my theta is 38 degrees. My hypotenuse is 14. And the side I want is the opposite. And I don't know what that is, it's x. Alright, now we've got the quantities that we're interested in. Let's go up and we'll see if we can find the ratio that will help us discover what this side is for the opposite, so x. So we've got so, ka, and toa. So the question is, which ratio here has enough known quantities for us to deduce the value of the opposite side x? So theta, we have that, it's 38 degrees, so it could be all of these candidates. But we have the candidate hypotenuse, so it's either these top ones, so sine or cosine, and we're looking for the opposite, so we're going to go for sine because it's got theta, opposite, and hypotenuse. So what I'm going to do is I'm going to write so sine theta is equal to opposite divided by the hypotenuse. Now, before I sub in any values, we want to solve for the opposite here. So what I'm going to do is rearrange this identity such that the opposite becomes the subject of the equation. To do that, I'm going to multiply everything through by h. So we're going to get h sine theta equals opposite, and then shuffling the expressions around, we get h sine theta. Alright, now that we're in the form we want, let's substitute in our values. So we've got x, in place of h we have 14, and then finally we have sine 38. Now, next step, we have to use our calculators to solve this. So I bring my calculator, and I'm going to go menu, exit 1, then I just have to set it to degrees. Alright, now putting the values in, I go 14 sine 38. It's going to yield the value 8.6192. I'm going to go to 2 decimal places because I think that's good enough for what we're doing. So we'll go 8.62. And we can't have quantities without units, so we'll call it 8.62 units like so. So this one here has been an example of how we deduce the value of x using the sine ratio. So sine theta equals opposite over hypotenuse. Now, let's have a go at deducing the quantity for y. So what we want is value for y, which is our adjacent. So we're going to put our quantities we know at the top. So we know theta is 38, hypotenuse we know is 14, and the adjacent is given the quantity y. So we've got the angle, we want the adjacent, and we have the hypotenuse. Let's look at our ratios. We've got so, ka, toa, we have the angle, we have the hypotenuse. So it's again either sine or cosine, but this time we want the adjacent. So it's cosine. Cos theta equals adjacent over hypotenuse, or ka. Alright, we want to rearrange in terms of adjacent. So what I need to do is multiply both sides by h. And therefore that will yield h cos theta is equal to the adjacent. And then shuffling the terms around, or the expressions around, we get h cos theta, like so. Alright, next step, we substitute in our values. So a is y, h is 14, and cos 38, so angle. And then we bring the calculator up once more, and we type 14 cosine 38. That will be 11.03 units. So that's example 1, where we've deduced the value of x and the value of y. First one using the sine identity, second one using the cosine. Alright, next example. We have this triangle here. We have an angle of interest, or a theta, of 64 degrees. Opposite the theta, we have our opposite side, which is 17. And then our hypotenuse is denoted by the variable x here. So we've got theta equals 64. Opposite equals 17. And hypotenuse is x. So now what we're looking for is a ratio that has theta, opposite, and hypotenuse. We go over, our candidate is the sine function. Sine theta equals opposite over hypotenuse. Now for this situation here, we're solving for h, and thus h is on the bottom here. So what we need to do is a bit of clever shuffling around. So once again, we multiply both sides by h, and that will yield h sine theta equals the opposite, and then we have to divide both sides by sine theta. That's going to yield h equals the opposite divided by sine theta. And now we're in the form that we want, so we can sub in our values. So rather than saying h, we can just throw in x equals 17 divided by the sine of 64 degrees. Now it is time to shine by putting these values in our calculators. So we're going to go 17 divided by sine 64. That's going to yield a value of 18.914, or 18.91 units. Now, one way to verify the answers that we're getting when we're doing trig is if we look at the sides we're working with, notice that in this one we're trying to deduce the hypotenuse here. To check the reasonableness of our answer, we can have a look and say it's 18.91. Then we compare it to the other sides we have in the triangle. The hypotenuse should be the biggest side, so it definitely needs to be bigger than the opposite here of 17. In which case it's 18.91, which means it's bigger than 17, and therefore we are reasonably okay to assume that this would be the right answer because it's bigger than 17. But this has been an example here of how we can solve when we have the unknown in the bottom of the fraction. Alright, example 3 now. We have this right angled triangle. The angle of interest is 61 degrees. So that's our theta. The opposite is denoted by x, and the other angle of the side of interest is the adjacent. The one that we're not using is hypotenuse. So what we have is theta equals 61 degrees. Opposite is unknown, and hypotenuse is 14. We're solving for the opposite. So what we need is a ratio that has the angle, the opposite, and not the hypotenuse, but the adjacent, I should say. So when we go over, we have so, ka, and toa. The candidate that we're looking for is tangent here, or tan. Tan theta equals opposite over adjacent. So we're going to write that as tan theta equals opposite over adjacent. Now we're solving for the opposite, so we're going to multiply both sides of this equation by the adjacent. That's going to yield a tan theta equals opposite. Then we swap the two expressions around. Opposite equals a tan theta. And now we substitute in the values we have. So the unknown is x, the adjacent is 14, and we're looking at tangent of 61 degrees. Alright, next step is we plug this all in our calculators. We're going to get 14 tan 61. Lo and behold, the answer is 25.26. In summary, this has been a video demonstrating how we can calculate unknown side lengths in right angle triangles using these three trigonometric ratios here.